The question that I have is, what is the equation that governs fluid flow through soil in 2D? So let's start with the derivation of the governing equations. Just to keep this realistic, I picked a specific seepage problem here, but the equations we derive here are going to be valid for any seepage problem as long as they are two-dimensional. So what I have here is a model seepage tank we use in most soil mechanics laboratory to teach the principles of seepage. We have a sheet pile wall here retaining water to its left, so the water is flowing from left to right like this. Let's introduce a 2D Cartesian coordinate system involving an x and y axis like this. And I'm going to take a small differential element and draw this to an exaggerated scale over here. The fundamental principle that we are going to use here to derive the equation is the conservation of mass. We are going to assume that the fluid is incompressible, which is a very good assumption for a fluid like water. We are also going to assume that the soil is incompressible. Usually seepage doesn't cause any compressibility of soil, and therefore this is a good assumption too. So because of these assumptions, the conservation of mass simply becomes conservation of volume, or more commonly called the continuity equation. Now looking back at this little element here, the continuity equation says the rate of volume of water that goes in must be equal to the rate at which the volume of water comes out of that element. Simply put, rate of volume in must be equal to rate of volume out. If we have a one-dimensional tube, we know we can calculate the rate of volume simply by multiplying the velocity by the cross-sectional area of the tube, right? So we're going to apply this principle to expand on this. To do that, we need to know the velocity with which the water either comes in or goes out of this element. Let's say the velocity of water crossing this face right here is v sub x. Then the velocity on the other side is going to be vx plus a change, and the calculus tells us that change is partial of vx with respect to x times dx. We have similar expressions in the y direction. So water comes in through these two faces and leaves these two faces. So to calculate the volume rate of water that comes in through this face, I just need to take this velocity and multiply that by the cross-sectional area of this face, which is dy multiplied by 1, where 1 is the thickness of this element, into the paper. So here is the expanded form of the continuity equation. Notice that I have vx times dy term on the left side, and I have vx times dy term on the right side. So they will cancel out. And I have vy times dx on the left side, vy times dx on the right side. So the equation simplifies to this. Let's say the total head varies like this with x and varies like this with y. Then the slope of this curve is the hydraulic gradient in the x direction, and the slope of this curve is the hydraulic gradient in the y direction. So now using Darcy's law, we can express the velocity in the x direction like this and the velocity in the y direction like this. Two things for you to note here. Number one, I'm using a negative sign here, right? That's because if the head increases this way, then the water flow is going to be in the opposite direction. To account for that, we introduce a negative sign here. Number two, I am using k sub x for the permeability in the x direction and k sub y for the permeability in the y direction, right? Now this is because a real soil can be anisotropic. That means the permeability in the horizontal and the vertical directions could be different from each other. So to keep things general at this point, we will use different permeabilities in these equations. So substituting these in this equation, the equation simplifies to this. But if I do have an isotropic soil, then kx equals ky, and then the equation further simplifies to this. If I don't, I need to do a coordinate transformation to proceed. This is something we do in advanced level courses. So we basically have a second order partial differential equation in H, and this equation is a very popular equation in the area of mathematics, and it's called Laplace equation. And it turns out there are a few other areas of physics where you run into the same equation. For example, conduction of electricity and conduction of heat are two examples where you end up with the same Laplace equation. Here are some of the different methods available for solving this equation. Direct mathematical solutions. So basically, you take the differential equation, integrate that, apply the boundary conditions to evaluate the integration constants, and then you have the solution. So we will illustrate this for the one-dimensional problem we discussed in the earlier video. There is a variety of numerical methods available these days, including the finite element method and the finite difference method. In most cases, you will use one of these methods to solve this equation. Basically, you look for a software package that can solve the Laplace equation and then interpret the variable, the results accordingly. Like for example, H here is the hydraulic head, right? But if it is a conduction of electricity problem, then you will have the voltage in place of H here. The third method is based on the analogy between the electrical conduction problem and the water flow problem. It turns out that you can do a little electrical experiment in a laboratory to solve the seepage problem. I won't go into the details of that here. In the fourth method, you basically make a physical model, conduct the experiment, measure the relevant quantities, and then extrapolate the results using the principles of similarity to get the corresponding prototype quantities. In fact, the seepage tank experiment that we normally do in a soil mechanics laboratory is one of those things. The graphical solution is one of the oldest methods, and we will spend some time on that here. It turns out that for most seepage problems, you can actually sketch the flow lines and the equipotential lines by hand and then create a flow net based on that. So once we have a flow net, we can then calculate most quantities that we would be normally interested in. Let me illustrate this first method, the direct mathematical solution method, by considering this one-dimensional problem. I'm going to take my x and y axes like this. Remember, we showed earlier that the total head does not vary across the cylinder, right? And therefore, total head is only a function of x. So this implies that the first and second derivative of h with respect to y must be equal to 0, right? Also, we can convert this partial second derivative into an ordinary second derivative. So we have a ordinary second order differential equation which can be easily integrated. So I'm going to integrate this twice. So we end up with a linear equation for h in x. In other words, total head varies linearly as you go from the left end to the right end of the tube, right? As long as the soil is homogeneous. Remember, this is what I pointed out earlier. Head varies linearly. Now we have a mathematical proof. We can find this integration constant C1 and C2 by applying the boundary conditions, which are at x equals 0, total head is 10 meters. At x equals L, total head is 5 meters. So the application of these boundary conditions lead to this linear equation. Here's a little graphical sketch showing the variation of h with x. It goes from 10 meters at 0 to 5 meters at 2 meters. So this mathematical method seems to lead to the solution in a fairly straightforward manner for this problem. But most realistic seepage problems are very complex, and the solutions by this mathematical method is very difficult, and therefore normally we don't use this method. We will not cover methods 2, 3, and 4 here, but we will talk about the graphical method in another video.